I'd like to begin by just saying thank you for giving me this opportunity to share what myself and my teammates have been working on for the past couple of years. I represent the MakerSat team here today. We are a group of undergraduate research students at Northwest Nazarene University near Boise, Idaho. Today I'm going to be talking about MakerSat, a CubeSat designed for in-space assembly. So I know that we're all aware that getting a CubeSat into orbit is a very difficult task. Some of those issues include the high costs, the lack of launch opportunities, and even the occasional rocket malfunction. So today, I'm going to propose a solution to some of these problems. We now have the capability on the International Space Station to manufacture CubeSats. Given a 3D printer, generic electronics that can be shipped on any resupply mission, we are now able to manufacture and assemble these CubeSats and deploy them from the International Space Station. The main objective of the MakerSat mission is to demonstrate in-space additive manufacturing of small spacecraft. Today I'm going to talk about three main points. First, I'm going to talk about the advantages of in-space manufacturing. Next, I'm going to talk about how to assemble MakerSat. And finally, I'm going to talk about some of the open questions about polymer degradation in space. So I'm going to begin by talking about the advantages of in-space manufacturing. The first advantage here is the reduction in cost. This reduction in cost is a result of a reduction in payload volume. Basically, we're launching raw material. Another advantage is the ability to iterate. By manufacturing in space, we're able to iterate more often, and this gives us an opportunity to work out some of the bugs. Also, by having generic boards launched to the International Space Station, this opens up the ability to reconfigure and customize these boards on the fly. Basically, upload new software with the click of a button. And last, this opens up a new design space. We no longer have to design these structures to survive high-G launch forces. Rather, we can design these very fragile or intricate structures, shown here, MakerSat, or the SpiderSat. So yeah, next I'm going to talk about the on-orbit assembly issues. A couple of important ones here are crew safety and crew time. In order to reduce the risk of crew safety, MakerSat has been designed to assemble without the use of any free-floating fasteners or tools. This leads to an assembly time of approximately 5 minutes on Earth. That may be a little bit more once we are on station. And finally, our material choice. So, you all know that polymers degrade in space. Given the materials that are available on the International Space Station right now, we have chosen to go with molten. It is a high temperature resistant material, very, very strong. So now that we've talked about the advantages of in-space manufacturing, let's go on to how to assemble MakerSat. But before I do that, I'd like to point out a couple of key features of the satellite. So we have 4 different science payloads. Each science payload is backed by a solar panel. Located on the top, we have the power system, power and communication system. And located on the bottom, we have the hub, or the main interconnect between all the science payloads. Last but not least, we have the 4 3D printed rails that are snapped into place. So 4 rails will be 3D printed on the Made in Space additive manufacturing facility. The additive manufacturing facility shown here is the first commercially available 3D printer in space, and it is operational as of a month or so ago. We will be printing 4 of these rails in the printer, and I'd like to point out a couple of key features of these rails first. Located on either end are 2 slots. These slots are going to hold the top and the bottom of the CubeSat in place. Located in the middle, we have a little clamping mechanism, and that's going to clamp everything together to keep everything secure. So the first step here, is to plug in all of the wiring harnesses. That is going to include the 4 science payloads and the power and communication system. Next, we're going to snap the rails into place. The rails are going to be snapped in the following configuration. Next, we'll snap in the 2 remaining science payloads, shown here. Next, we'll bring the top and the bottom of the satellite towards the center and slide them into their respective slots in the rails, shown here. And last but not least, we'll take the remaining science payload and snap it into place, securing the CubeSat. So now that we've talked about the benefits of in-space manufacturing and how to assemble this satellite in space, next I'm going to focus on the multi-user aspect of MakerSat, or the science payloads. So as I mentioned earlier, the hub is the main interconnect between all the different science payloads. The hub acts as a multiplexer, which it multiplexes power and radio communication to each payload in a round-robin fashion. You see here that we have 2 different payloads from Northwest Nazarene University. We have 1 payload from Caldwell High School, and on the bottom here we have 1 payload slot that is currently still available for a highly motivated student team or other institution. So I want to ask you guys, if you guys had that slot, what would you do with that? What kind of science could you do on that slot? So I'm going to turn my attention now to the first experiment shown here, the polymer mass loss experiment. Polymer degradation in space is a major concern. The mechanisms of polymer degradation include ultraviolet radiation, ionizing radiation, outgassing, and monatomic oxygen radicals. So shown here we have the MISSI-2 polymers experiment. This experiment was placed on the outside of the International Space Station for approximately 4 years. And what it did was measure the erosion of different polymers. And as you can see here, that some of these mass samples are completely eroded after 4 years. The problem with this experiment is that they only got 2 data points, one from putting it out there and then once when they got it back in. So the MakerSat satellite is going to attempt to do this real time by taking multiple mass samples. We'll be measuring the mass loss of different samples using a cantilever beam. So the resonant frequency of this cantilever is used to determine the polymer mass loss. So if we look at this diagram here, we have a small vibration motor used to mechanically excite the cantilever beams. Each cantilever will have a different mass sample placed on the end. When it is vibrating, the piezoelectric sensor will produce a waveform. That waveform will be run through an analog to digital converter and then through an FFT algorithm to determine the resonant frequency. So shown on the right here is the actual implementation of the experiment on the payload board. You'll notice that we have 3 different cantilevers. The red and the blue mass samples here represent the ultum and nylon samples. The cantilever in the middle will have a brass sample. That will be our control sample. So looking at some of our first results here, the top graph shows the relationship between the resonant frequency of a cantilever with respect to the mass placed on the end. It states that the resonant frequency is proportional to 1 over the square root of the mass. We can see here in our preliminary results that our method does indeed follow this theory. So far, we have been able to detect a mass loss of approximately 1%. So given our 500 milligram mass sample, we can detect a 5 milligram change. Shown on the bottom here is our expected results. As time goes on, we expect to lose mass. So as that mass is lost, we expect the resonant frequency to increase. So moving on, looking forward, MakerSat is now becoming a reality. We are currently manifested on the Alana 20 mission, set to launch in 2017. We are also currently working with Braden Space on an ISS-based mission where we will actually manufacture and assemble the CubeSat in orbit. So to conclude, I just want to remind you what we went over today. I talked about the advantages of in-space manufacturing. I talked about how to assemble the CubeSat in space. And last, I talked about the open questions of polymer degradation in space. So I have a picture here of Caldwell High School. Caldwell High School is taught by Mr. Zatiro, who is somewhere here in the audience. There you are. So through the MakerSat platform, we are giving students like these the opportunity to fly their science payload in space. Without a platform like this, these students would have no access to space. So the MakerSat mission is trying to open up that access. So with that, I would like to end with a quick demo of how to assemble the CubeSat in space. And I'll be honest, I'm going to cheat here a little bit. For purposes of this demonstration, I have not included the wiring harnesses, so you can expect to add a couple of minutes to account for that. So first I'm going to snap all of the rails into place, as so. Each of these has a nice audible snap that you can listen to. Next I'm going to plug in the two remaining science payloads, as so, basically making a three-sided cube. Next, I'm going to take the hub and the power and communication system and slide them into their respective slots. And last but not least, we'll take the remaining science payload and snap it into place. As so. So with that, I'd like to give a shout out to our funding here at Northwest Nazarene University and the Idaho Space Grant, and I'll open up to questions.
You're being built in space, why do you need to conform to the CubeSat form factor?
That's a great question. So we're conforming to CubeSat form standards. Basically, there's different options to deploy from the International Space Station right now. There's nanoracks, there's JSOT, I believe. So with that in mind, it's a way to deploy from the space station. Yes?
Where are you going to fly on the Lana mission?
We are currently manifested on the Virgin Galactic Launcher 1.
You're going to fly that frame?
Yeah, that's a great question. Are we going to fly this frame? So, in order to fly this frame, we're going to have to go through all of our qualifications and testing. If that does not work out, we will always fall back to the aluminum rail. But keep in mind that the ultimate goal of this is not to actually launch this design. This design isn't necessarily designed to be something that is launched. Rather, it is designed to be printed and launched from the ISS. So it's not going to need to withstand those high G launch forces. Yes?
What's the reduction in structural ratio that you can get from this assembly in space?
Okay, in terms of mass?
Yeah, with the ratio.
Yeah, so traditional structures are anywhere from 100 grams to 150 grams, I believe. Right now we're sitting at about 50 grams with our rails. Yes?
Could you point out the high school teacher again?
Yeah, right back here.
So my question is, how are you going to get software and things of that nature into the system, and who's going to put it together on the space station? Your astronauts going to have time to do all that?
Sure. So software is going to be downloaded when we launch our electronics in the first place. And then crew, as far as crew time, I know that it is very hard to acquire, and we've put a lot of focus into making that as simple as possible. All right, thank you.